Okay, as always, guys, thank you for your hard work on the group work. I have the solutions to this in Canvas. So be sure to keep rehearsing it, revisiting it, try it again, maybe on your own in sometime over the break. Just to make sure you really are solid on this. Okay, all set. What I want to do next is talk a little bit about the question of who cares if a matrix is diagonalizable. Like, that is a reasonable question for us to have. I'd like to address that a little bit. So this is actually in the section 7.3. And this is part of what your homework for next Tuesday will involve. This is called diagonalization. Okay, so if a matrix is diagonalizable, then we're going to be able to talk about this thing called diagonalization of the matrix. So let me see if I can kind of explain this for you. Here is the setup, guys, that we're going to have. The setup of this is going to be, let's assume that A is an n by n non-defective matrix. And again, non-defective just means diagonalizable. It's just another word for the same thing. So assume we have a non-defective matrix. Again, what does that mean? That means that every eigenvalue pulls its weight. Yeah, which means that in total, this means that A has n linearly independent eigenvectors. Because there's going to be a total of n eigenvalues for an n by n matrix. So if it's a 3 by 3, you'll have 3 eigenvalues. If it's a 5 by 5, you'll have 5 eigenvalues. Now, when I say that, I'm including repeats. So sometimes these eigenvalues are repeated. But A will have n linearly independent eigenvectors, and I'm just going to give them names here. Let's say V1 all the way down to Vn. Okay? Each of those eigenvectors, of course, has to have some kind of a companion eigenvalue. So let me just kind of label those here as well. Lambda 1, lambda 2, all the way down to lambda n. They always come as a pair. You can't have an eigenvector without an eigenvalue, and you can't have an eigenvalue without an eigenvector. So let's just suppose we have that sort of correlation between eigenvalues and eigenvectors. Some of these lambdas might be repeated. Remember that it's still possible for a matrix to be non-defective even if some of the eigenvalues are repeated. Okay, so that's important to keep in mind. But here is what we're going to do. We are going to take this setup that I've just put on the board, and we are going to just sort of out of the blue form a new matrix, which is going to be called S. And this is also going to be the same size as A was, n by n. And the way we're going to make this matrix S is we're just going to put these eigenvectors, right? We're just going to lay them into the columns of this matrix that we're building. So each eigenvector now, this is sort of the new material for this section. Take all of these eigenvector pairs, which we've learned how to find in the last couple of lectures, and just take the eigenvectors and lay them down in S. Okay? So you're going to want to remember this. This is how S is formed. We just simply, if you've done all of the work to find the eigenvectors, this is kind of just, you can do this without breaking a sweat. You just lay the vectors into the columns of this new matrix that you're building. Okay, so that's the starting point. And then from there, what we have to do is the following. Then we're actually going to calculate A times S. Now, at this moment, you probably have no idea why I'm doing that. There's no reason to think that this would be anything interesting, except that I know that it's interesting. That's why I'm doing it. excuse me, so what I'm gonna do is I'm just going to multiply A times S, and here's what S is. S is just that matrix I just created, like that. Now, when I do this matrix multiplication, by now I think we all hopefully are remembering that we do that by taking dot products of the rows of A with the columns of S. Well, if you do that kind of in this framework here, if I ask you what's the first column of this product going to be? The answer is you're just going to be dotting the rows of A with V1. Just V1. And that becomes the first column of A times S. It just becomes A times V1. And then similarly, the second column is just A times V2. And dot, 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 all the way to the end, we get A times Vn. So far, so good? Again, as of now, you're probably sitting there thinking, I have no idea why he made S like this. I have no idea why he's multiplying this out. There's going to be some incredible epiphany in just a minute. Okay. Now, does anybody know what A times V1 is? What would that have to be equal to?
Lambda V.
Lambda 1 V1. I'm glad you remembered the most important equation in chapter 7. I keep harping on this one, right? A times V is always equal to lambda times V. So AV1 becomes lambda 1 V1. And AV2 becomes lambda 2 V2. And dot, 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 dot. The last one is lambda n Vn. And what this is it's actually just the matrix S with its columns being swelled up by different scalars. The first column has been multiplied by lambda 1, the second column has been multiplied by lambda 2, and so on. And I wonder if I could just, over here on the side of your notes, don't do this in the middle of your calculation, but I just want to show you an interesting little thing. If you take any matrix, I'm just going to show a 2x2 illustration of this. And if you right multiply it by a diagonal matrix that has some numbers down the diagonal, like that, if you actually work this out by using your usual dot product matrix multiplication procedure, let's look what happens. So for the 1, 1 entry, I take the first row and I dot it with the first column, and I just get 2A. Right? The 1, 2 entry, I take the first row and dot it with the second column, I get 5B. And then on the second row, I'll get 2C, and on the bottom right corner, I'll get 5D. Look at what happened. The original matrix that we have here on the left had its first column get multiplied by 2, and its second column got multiplied by 5. When I put a diagonal matrix on the right side of it with those numbers in it. What I'm trying to say, guys, is that right here, we can take this and treat it as if we had our original matrix with just V1 through Vn. And if we right multiplied it by a diagonal matrix that has all of those lambdas on it. That's supposed to be a diagonal matrix. I did not draw that very well. Let me try one more time. So this is going to be a nice diagonal matrix here. Lambda 1 and then lambda 2 and dot, dot, dot down the diagonal to lambda n. Everything else is zeros in that matrix. So when you take a matrix and you right multiply it by a diagonal one, it has the effect of swelling up those columns by those diagonal values. As exactly as this is showing here with one example. Everybody with me? So quiet here. Are we sure we're okay with this? If you're okay with it, then what you probably realize now is that although I started with A times S, I have now ended up with the S on the left being multiplied on the right by a diagonal matrix, which I'm going to call D, where D is equal to this diagonal matrix with the eigenvalues going straight down the diagonal. That's the point. So if you've done the work to find all the eigenvalues and eigenvectors, then it's very easy to write down S. Its columns are the eigenvectors. And it's very easy to write down D. It's just a diagonal matrix with the lambdas going down the diagonal. And A times S is equal to S times D. So just in summary, A times S is equal to S times D. That's basically the upshot of it. I still haven't really convinced you that this is a cool thing or that this is a big deal. Okay, so what? A times S equals S times D. Who cares, right? Who cares? Well, I actually want to make one more comment about S over here. These columns are consisting of the eigenvectors. And these eigenvectors are Li. So you're talking about a square matrix whose columns are all Li. Well, what kind of a matrix would that be? Say it again. Invertible. It would be invertible. Do you guys remember our invertible matrix theorem? If all of the columns are linearly independent, then that would mean that if you did EROs, you would get pivots going all the way down the diagonal. So this matrix S is invertible. I want to point that out. That's because its columns are Li. Now, if my matrix had been defective, I would not have had n of these vectors to be able to build out this n by n invertible matrix. Okay, so we really are relying on having a non-defective matrix here to begin with. Okay? So here's our summary, and I just got done saying that the S is invertible. So that means, for example, that I can play with S inverse. I can take this equation, and you know what I'm going to do? I am going to put an S inverse on the left side of both sides of the equation. So I can take AS equals SD, and I can put the S inverse on the left of it, and this becomes S inverse AS equals D. This one also is probably worth, well, yeah, this is really one that you'll want to know. Excuse me, the S inverse does need to be on the left, and then the A, and then the S, and then the D on the other side, okay? Or, instead of multiplying the S inverse on the left of this original summary equation, I could also put it on the right side like this. So I could put A times S inverse equals S times D times S inverse. And again, I can cancel. See, I'm canceling the S inverse with the S. So this time I get A equals SD S inverse. This is also correct. And it's easy to forget which side to put the S and the S inverse on. So you kind of have to like memorize that a little bit to keep it straight. But those are both correct. Am I allowed to get, you saw me canceling the S inverses here. Can I do that here too?
No.
Not if there's another matrix in between. Actually, if you canceled the S and the S inverse here, what would happen? This is illegal. If you tried to cancel them here, what you would end up saying is that A equals D. Well, chances are A did not start off as a diagonal matrix in the first place, right? So it's probably not reasonable to think that we're going to cancel the S inverse S and just get A equals D. That's not the case. Right. So just something to keep in mind. We cannot cancel an S with an S inverse unless they're right next to each other. Like the way they are here. If there's another matrix in between, it just can't be simplified. With me? Now, you still might wonder what's so great about this. So I have my diagonalizable matrix, which means I can write down S, I can write down D. I know how the matrices are related to each other, right? But let's just, as an application, let's just suppose that I want to calculate some huge power of A. I want to take the matrix A and I want to raise it to some big power, right? So let's just say computing powers. Let me give you, I'm going to verbally give you an example of this, but then to see the details, I'm going to have you watch a video. I'm not going to go through it. Let's imagine that there are two sections of Math 250B. I want to get real world example here. Two sections of Math 250B. And we won't write this down right now. Just want to kind of think it through. Every single day, 10% of the students in section 1 switch to section 2. And every single day, 20% of the students in section 2 switch to section 1. So you have these two sections of Math 250B, and the students are kind of, figuring out which section they're going to be in. And they swap back and forth, and they do this every day, right? And let's say they do it every day for the entire semester. Okay. God, I hope that never happens, right? The question is, how many or what fraction of the students end up in each professor's class by the end of the semester? It seems like more students are flowing that way than flowing that way. They're not going in equal ratios, right? Well, it turns out that that process of students switching sections can be modeled as a matrix. You can write down, if it's only two sections, there would be a 2x2 matrix that would model that scenario, right? And when you multiply by that matrix, you effectively do the process of the students switching sections. And you would like to know, well, what happens at the end of the semester? Well, that would be doing that matrix almost infinitely many times. That matrix once, twice, 3 times, 4 times, 5 times, every single day, you want to calculate big powers of that matrix, right? It's called a Markov process, and it is a great application of what we're talking about here of being able to compute a power of a matrix. How does it work? So this is where you can maybe write this down now, because this is kind of just the simple little punchline of it. If I want to raise a matrix to a power, let's say the kth power, well, I have my formula. This is assuming that the matrix was diagonalizable. So assuming that the matrix was non-defective, I can find S and D such that this is true. Okay. Now the question is, can I calculate this? This looks horrible. Let's just see S, D, S inverse multiplied by S, D, S inverse multiplied by S, D, S inverse. And you do this K times like that all the way to the end. That's a lot of matrix multiplications. Excuse me. But what do you notice that you can do with that to simplify it? By the way, the parentheses don't matter. When you're doing matrix multiplication, you can't switch the order of anything, but you also don't really need those parentheses there. So if you didn't want to write the parentheses, it would just look like this. Right? So now there's no parentheses. What do you notice that I can do, Robin? Yeah, in the middle of all this big alphabet soup of matrices, you do have S's and S inverses right next to each other. Here's S inverse and S. Here's S inverse and S. Here's S inverse and S. It's all canceling out. And what is actually left over? I've got an S in the front, and then I have D, 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 a whole bunch of D's. That must be K of those. And then there's one leftover S inverse at the end. Right? Guys, if you want to calculate powers of a diagonal matrix, as opposed to A itself, which is some messy matrix, if you want to take powers of a matrix like this, it's easy. You just do the powers of the diagonal values. So if I had, 2005 and I want to multiply it by 2005, if you just do your matrix multiplication, you'll get 40025. It will just simply square the diagonal entries, which is really, really nice. This is just S times the matrix whose diagonals are just getting powered up to the kth power. Everything else still 0, and then S inverse. Oh, well, that's not so bad then. All I have to do to calculate the kth power of A is take the kth power of my diagonal matrix, and then of course I have to put the S and the S inverse in there. That's it. That's the whole story. So it's not so bad. It's really not so bad to do that. And again, if you're talking about how many students are in each professor's class at the end of the semester, you're going to let K go to infinity, for example. This is how a semester usually feels by the end of it, right? Well, if these lambdas, so for example, if the eigenvalues were like fractions, if they were like between 0 and 1, which they often are in these Markov processes, if those lambdas were fractions, then by the time you start powering them up, you guys all know that if you take a number less than 1 and start raising it to higher and higher numbers, it tends to go towards 0. So this matrix could potentially become extremely close to the 0 matrix. And that might further illuminate your physical problem that you're addressing at that time. Guys, the types of people who are interested in eigenvalues and eigenvectors is not just a pure mathematician like me. Economists care about it. Statisticians care about it. Anybody doing business and finance cares about this stuff. Physics cares about eigenvalues and eigenvectors. It's a very, very mainstream topic that we're learning about in a math class, but which has lots and lots of applications. That switching sections of 250B is kind of a silly application, but you can imagine in the real world those kinds of what are called dynamical systems at play, where you have different quantities that are sort of, this is another silly one. You have a bunch of people sitting around the Thanksgiving dinner table, and every 5 minutes, they each steal some of the food from the plates of the people on their left and on their right. And they do this over and over again. And the question is, well, where does the food end up at the end of the meal? Because this process, this dynamical system just evolves again and again and again over time. So this is not just sort of a fly-by-night thing that has no real application. It's quite interesting to a lot of different fields, not just math. So anyway, I will kind of go light on that though. You're not going to get homework problems about the Markov processes or anything. I'm not going to go off topic too far in that direction, but I do want you to know that those applications are there. What I'd rather do before we take a break today is do one example of finding this S and the D, and just making sure everybody can do this. And I'm actually going to do one of the homework problems for tomorrow. So let me do it here. So we're going to do one example. So far, so good? Any questions yet? All right, let's do one example. And this is actually being stolen from your homework assignment for tomorrow night. So I'm doing one of these problems for you. And basically, here's what it says. They're going to give you this matrix A, which I'm going to do right now. 3, 0, 0, 2, 0, negative 4, and 1, 4, 0. And my question is going to be determine if A is diagonalizable. Remember, that just means non-defective. Determine if the matrix is non-defective, and if so, find S and D such that, so if so, find S and D such that S inverse times A times S is equal to D. Okay. Right. So I tried to keep the key points on the board. The D is still on the board here. Here's the S. We know how to do that. So your homework problem for tomorrow is not asking all of this. The homework problem for tomorrow just says find the eigenvalues and eigenvectors. But that's the first step, right? That's the first step to doing this problem is we have to find the eigenvalues and the eigenvectors and sort of see what's happening, okay? So let's start solving this out. There's a lot that goes into this. Definitely a lot that goes into this. The first thing we need to do, pretty much always the first thing we need to do is find the eigenvalues of our matrix. Okay, so we have our characteristic equation, which is where we're going to take a determinant. And I'm going to subtract my lambda off of the main diagonal here. Okay, so this is how we start off doing our determinant. Unfortunately, this is not a triangular matrix, so I can't just read off the lambdas. I have to actually work them out in this case. And do I have any suggestions for how to simplify or how to evaluate this determinant here? This is a 3x3 matrix. Do we have any suggestions? Cofactor expansion. Yeah, what row or column do you like? Yeah, the first row, yeah. And that's because of those zeros. So I'm going to expand row 1. Excuse me, because we have quite a few zeros there. So if I go across the first row, I have a 3 minus lambda here. And then I'm going to cross off that row and column. And then here's my little 2x2 submatrix. If I look at that little 2x2 submatrix, I have lambda squared plus 16. So this becomes lambda squared plus 16. And of course, there's a minus 0 and a plus 0 that we're not going to worry about. This is what we're going to have. And we have to set this equal to 0. This determinant here should be set equal to 0 now. Okay. So can anybody help me with that? What are the what's the first lambda value that you see? 3, right? Yep, 3. So that's right here. Lambda equals 3. And then the other potential place to get the eigenvalues is from this term. Lambda squared plus 16. What are the lambda values for that would create lambda squared plus 16? How's that? Not 4 and negative 4, actually.
4.
What's that?
It's just positive 4.
No, not positive 4, not negative 4.
Wait, it's
4i and negative 4i. This is
Yeah,
going to have
yeah.
imaginary roots, guys. It's not minus 16, it's plus 16. If you're not sure, you can always go back to that quadratic formula, right? That's your go-to
Oh, yeah.
method for coming up with the roots of any quadratic equation. This time we're going to get plus or minus of 4i. If you square plus or minus of 4i, you will get negative 16. And then when you add that to 16, you'll get 0. So that's
Oh,
the
yeah.
point. Everybody good with that? By the way, you can also check your fun facts. The trace of this matrix is 3. So my lambdas should add up to 3, which they do. And then if you do the determinant of this matrix, I think you would just end up getting 48. Well, if you take 3 and you multiply it by 4i and minus 4i, if you work all of that out, that should be 48. that should be 48, because the two factors of I, we know that I squared equals -1. That cancels the minus sign, and then 3 times 4 times 4 is 48. So the numbers are making sense to me. Okay, guys, the first sentence of the question that we're answering says, determine if A is diagonalizable. Can I answer that part of it already?
Yeah,
Yes, we can. And what is the answer?
yeah,
It is because
there's
no
different.
repeating.
there's
repeat.
no repeating eigenvalues. That's right, there's no repeats. So this implies no repeats, no repeat lambdas, and that implies diagonalizable. So that is good news. That is good news. So we'll go ahead and check that off. That is true. Okay, now we have to actually find the corresponding eigenvectors, right? If I want to form the matrix S, the matrix S has the eigenvectors set up into its columns. So I need to find those eigenvectors now. Okay, so let's see if we can do that. Slow me down and ask me questions, guys, if you have any. I kind of love this stuff, so I go a little bit like I'm on a roller coaster. I get excited very easily by math in general. Doesn't matter what the subject is. Seth?
So the trace of A should be equal to the sum of the eigenvalues.
That's it. Yeah, that's one of our fun facts that I wrote down. If you add up all of the lambdas, they should add up to whatever the diagonal of A adds up to. It's just a way to kind of check that your lambdas at least look like they're reasonable.
The 3 is equal to 3.
Exactly. So that reassures us that at least these lambdas have a chance of being correct. It's not a guarantee, but at least it's a nice, check it off to make sure that that does work.
3 plus or minus 4 administrative numbers is 3.
If I take 3 and I add it to 4i and then I add that to -4i. So if I add up these 3 lambdas, I just get 3, which is the trace of that matrix. Yeah. Exactly. Okay, guys, let's figure out the corresponding eigenvectors. Let's start with 3. Lambda equals 3, since it's doesn't have any imaginaries in it. So here's where we have to do the null space part, right? So we're gonna make a null space. And let's remember how this works. I have to subtract lambda off of the main diagonal of A. So if there's the matrix A and I'm subtracting 3 off of the main diagonal of A. So we're going to get 0, 0, 0, and then 2, -3, -4, and then 1 and 4 and -3. Okay. Another little check that you can make for yourself is that this matrix should never be invertible. And we have a row of zeros here, which is a pretty much a clear telltale sign that it's not invertible. We're going to cross off that row. I'm going to do a quick ERO here. I'm going to move the bottom row to the top because I kind of like using that 1 as a pivot. The row of zeros, I'll put it way at the bottom. And then I'm going to do another step at the same time, if you don't mind. I'm going to take negative, I'm looking at these two numbers here, the 1 and the 2. I'm going to take -2 times the 1, 4, -3 row and add it to the other row. That's going to put a 0 there. Okay. So 4 times -2, add that to -3, we get -11. And then -3 times -2 is 6. If I add that to -4, I get 2. This we will just circle kind of as if it was a pivot as well. That's more or less what we're looking for. We can write down X, Y, and Z as our variables here. And I have a free variable, namely Z, right? So Z is free, I'm gonna call it T. And then remember that each of these other rows is really coming from an equation. So the second row is just -11y plus 2z equals 0. That's what the middle row of my row echelon form is telling me. So if I've decided that z is equal to t, then I can solve for y. I just have to move this 11y to the other side and then divide by 11. It's going to be 2/11 of t. Okay, and then I have the top row here. The top row has an equation x plus 4y minus 3z equals 0. That's what that top row of numbers is creating for an equation. And I need to solve this for x right here. So to do that, I have to move everything else to the other side of the equation. Let me just do it right here. So the x is going to be 3z minus 4y. And I'm going to plug in what I know. I know that z is equal to t. And I know that y was 2/11 of t. And if you clean that up, 33/11 minus 8/11 is 25/11 of t. So hopefully I'm doing my fractions well today. That's x, y, and z. And using that, I can make my eigenvector. I'm going to call this one v1. And it would be 25/11. I'm busting out the t, guys. I'm busting out the t. And I get 25/11, 2/11, and 1. Okay. Now, this is an odd numbered problem. You'll be able to check in the back of the book. And in the back of the book, you find out pretty quickly that they didn't put any fractions in there. And that's because it's perfectly okay to scalar this vector through by anything you want. In other words, you didn't really just have to like bust out the t and turn it into a 1. You could say, I'm going to let t equal 11. If you let t equal 11, then the vector would have been 25, 2, and 11. That's also fine. It's just a scalar multiple of this one. Remember, guys, the eigenvectors, they form a subspace. They're closed under addition and scalar multiplication. So if you take a legitimate eigenvector and you multiply it by a scalar, such as 11, you'll get another eigenvector. So don't expect that there's just only going to be one right answer here, right? You can get lots of right answers on this. Okay, now the real reason I chose to do this problem from your homework, though, is because we have a couple of imaginary lambdas, and I want to show you what happens with that. You probably think that that's going to be a nightmare. Actually, this was the worst one. Let me show you why. You're going to have to watch this closely, guys, because it will be a nightmare if you don't see some of these tricks that I'm going to show you. Let's take 4i. I have to do a null space to go along with that eigenvalue. I'm going to subtract 4i from the main diagonal of my matrix that I started with. So that first row becomes 3 minus 4i, 0, and 0. The second row becomes 2 and minus 4i and minus 4. And the third row becomes 1 and 4 and minus 4i. So this is my matrix, and we thought null spaces were bad when we had all real numbers in them, but actually this looks even worse, except it's going to be, I'm going to make this easy. I'm not going to do a single ERO. I am not going to do a single ERO. First thing is, I know that this matrix cannot be invertible. If I go through the ERO process, some row has to get zeroed out. And so we can kind of just preempt that and cross off a row now. Save ourselves some stress. Is there a row here? By the way, I'll label my columns. Is there a row here that you think would be a good one to cross off?
The middle one.
The middle one. Why do you say the middle one?
Because it's basically like the third one, except I like the third one more because it has a 1.
It's beautiful. Exactly. We have a pivot here, which is already a 1, so I kind of like having that there. The other thing is I was doing this problem. There were some people outside my office doing this problem yesterday, and they were trying to cross off the first row. And what I said to them was, actually, the first row is kind of your friend. The first row is really nice. What does the first row say? The first row says that 3 minus 4i times x plus nothing times y plus nothing times z adds up to nothing. If you look at that first row, so this just goes away. If you look at this first row, the x value is just 0. And I just love being able to write that down without having, I didn't really have to break a sweat to come up with that, right? That was an easy one to get. If I had crossed off the first row, it would not have been wrong to do that, but then I would have been living with 2 semi-complicated equations to deal with, right? So I'm much happier just keeping the first row. Now let's write down the third row. This is the other one that we're gonna keep. This one is x plus 4y minus 4iz adds up to 0. Again, why are these equal to 0 over here? That's because we are doing null spaces. Null spaces always involve setting equations equal to 0. Oh, but I already know that x is 0. We worked that out previously. So what am I left with here, guys? I've got 4y minus 4iz equals 0. Let's cancel the 4 and let's just solve for y in terms of z. It would just be y equals iz. Just look at this little part right here. Y equals iz. So I'm feeling pretty good about letting z be my free variable, which is t. And then y just becomes it. So y is just I times whatever z was. And so this is what we have. And so now I can write down my second vector, v2. My second vector is 0, I, 1. I busted out the t. So if I bust out that t, I just have a 0 for x, an I for y, and a 1 for z. Everybody following that? Okay, we're almost done, guys. This is the hardest part of the problem, is to just get these eigenvalue, eigenvector pairs. What about the third one? The third one is lambda equals negative 4i. Does anybody remember, did I say anything about these complex conjugate eigenvalues and how to kind of get the other eigenvector now? I actually claim that we can write it down and we don't have to do any work. We don't actually have to do another null space for this. We could if we wanted, but we would be working harder than we need to, right? We can just write down this vector. Do you remember how we do it? Once we have this vector, what do?
Copy it over.
Copy it over how? It's not the exact same vector. You remember?
Yeah.
What is
We
it?
add a negative to the I.
Right,
Only
that's
to the I, because it's the complex conjugate.
the conjugation. That's exactly right. We're conjugating this eigenvalue, so we have to conjugate this eigenvector. So I'll just remind everybody, all that means is that the imaginary parts of these entries have to have sign changes. The real parts stay the same. So the 0 on top stays as 0, and the 1 on the bottom stays as a 1, but that I right there turns into negative I. Okay, so I did go over that on Tuesday. Make sure that you, when you're dealing with these complex conjugate examples, you need to remember that you can save a lot of time if you just conjugate the eigenvector that you got with the other eigenvalue. Is that all right with everybody? Okay, so let's try to write down S and D now. Okay, so now I'm ready. It says find S and D. I almost erased it. Find S and D. So I think we can do it. Let's write down S here. And D, and then we'll take a little break. So for the S, we lay out the vectors into columns. So what do I got? V1 was 25/11, 2/11, and 1. And then V2 was it 0, I, and 1? And then V3 is 0, negative I, and 1. And then the D is just this diagonal matrix here with the lambdas down the diagonal. So there's a 3, and then there was a 4i, and then there was a negative 4i. Everything else is all filled in with zeros. Like that. This would be it. Now, some people don't always quite get the instructions on this correct, so just to help you out, they do put this equation into the question, but you don't actually have to find S inverse. And you don't actually have to do this multiplication at all. This is just kind of reminding you of what the relationship is between the S inverse, the A, and the D. So on these problems, when it says find S and D, guys, this is all you have to do. Nothing more than that. You don't have to like multiply this out or find S inverse. It's tempting to do that. If you were really trying to like do the Markov application, yeah, you'd have to find the inverse of the matrix and all that, but I don't think I'm gonna be asking you to find the inverse of this anytime soon. Okay. I do have one other question for you, which is, would this be the only right answer? I already said that you could scale multiply the eigenvectors as much as you wanted, and that would be fine. Other than that, would there be any other sort of different right answers that we could maybe have for this? What if the person next to you decided to find this eigenvector first, and then find this one second, and then come back and find this one third, right? There's really no preferred order, is there? It's not clear like which one's coming first, which one's coming second, which one's coming third. I actually claim that you could get different answers by simply putting these in a different order. Let me just give you an example. What if I did 0, negative I, and 1 there? And then I did 25/11, 2/11, and 1. And then I did 0, I, and 1. Right? That's still fine, right? And so then would we just have this? Careful, I'm making a mistake on purpose. See if anybody's paying attention. Guys, if I shuffle the columns of S around, which is what I did right here, that's fine. But you must shuffle the diagonal lambda values in a compatible fashion. So what I would have to do, if I'm going to list them in this order, then I got to go back and say, oh, this first column was for negative 4i, the middle column was for 3, and the far right column was for 4i. So this is fine to do that shuffling, but you've got to be compatible with both S and D on that. So here's one correct answer, and here's another one. So anybody could choose to shuffle these columns in whatever order you prefer, as long as you shuffle the lambda values in a compatible fashion. They have to go in the same order, is what I'm trying to say. Okay, so that's all. That's diagonalization, guys. That's the whole deal, right? We set up S, we set up D. If you can figure out how to do that, 95% of this was the stuff we already learned how to do. Finding these null spaces, right? Getting all of the free variables busted out, all that good stuff. It's all, the only new material here, guys, is actually writing down the S and the D. And here's how you do D, and here's how you do S. I can't paint it out any more sort of straightforward than that. That's basically it. That's basically it. Okay. All right. Why don't we take just a let's take a short break today, maybe 5 to 7 minutes. See if you can do what you need to do, and then I want to save 20 minutes to preview something totally new. So let's take a break, and we'll come back in a few minutes.
Yeah, fractions, he.
No, I changed the assignment. It should be gone by now.
Yeah.
No, I changed it because I wasn't gonna do the lecture on it, and then I decided, it's just what I just did right here. It's okay if you submitted it, it's not.
I would watch.
So you always got president.
That's why I had to get really good at using the picture.
Oh, damn, yeah. Bored. Oh, yeah, dude, those suckers. Like. Because I wanted a meal.
I was like, I'm all of a sudden you're like,
You're walking.
and then like, I was like,
Oh.
It's so obvious, so.
Well,
Wait, what? Like, the middle of like, there's just like,
what?
plates and the good walk exam.
That's wild. What?
Yeah, no.
I like it.
Yeah, that's weird.
Oh, yeah, you chickened up, nice. Yeah.
Professor agreed with you.
Yeah, that's
You guys gonna do the letter things and do? Yeah, you get to write letters that are me too. We're gonna last and not have break. The last time we found something, everyone like, okay. I'll probably go this way, I think, go park it.
Oh, there.
Yeah, there's no parking here anyway.
Yeah.
No, I don't think so.
Oh.
It's good. It's like this first. That view, I didn't know.
This first semester, yeah.
Oh, God.
It's just like so rough.
We're back to linear differential equation. Oh, yeah. I love that.
So far, only grade.
Not a big deal.
Not even an exam. Most of them.
I heard you guys are not moving in the
So
basement.
it's better than the stuff on exam two.
Most likely.
It's better than the stuff on exam two.
Yeah.
Oh my god, I hope to God I don't have to do that again.
Yeah. I gotta finish homework tonight.
Gotta meet with a professor. I'm gonna try to.
Oh, we should. We should. Interesting. Yes. We're doing like our second assignment. So far. That's right. And I saw that too. I'm trying to meet the computer science professor. So I'm trying to see if I can pop it up, introduce myself. We've not met him once, but I want to see if we can do actually research.
Wait, Dr. Pete?
Yeah,
Okay,
I'm gonna try to talk.
Dr.
Nangadam?
talk to Dr. George as well.
Okay.
Um,
I think Dr. Pete on those hours, right? I haven't. My friend told me that. I don't know about. What gave you that idea? You got research in?
Yeah, I would like to talk to him.
One, because of the project, the transfer program I'm in, I made good friends with this guy, he recommended talking. And I already met with the guy once, for advising my career. So I just felt like, why not? So.
Maybe. I don't know that I've talked this.
Maybe other.
Might be a good idea to reach out anyway.
Y'all got Smuckers? They sell that? I didn't have. How are you? I like the particles. They call it go back.
My math's already hard enough. You got
Some of them was. Some of them were.
Oh,
You got mud? Oh. So, I don't know to buy this one. What happened? Stick them up.
All right, everybody, I think it's been almost 10 minutes. I tried to give, was that about 10 minutes?
I think so.
I think so. It was probably pretty close. Let's go ahead and gather back up here again. I pretty much have said everything I want to say about eigenvalues and eigenvectors. In case anybody thinks it's going away and that we're never going to hear about eigenvalues and eigenvectors again, aha, we're just going to have to wait.
Yeah.
It's all coming back. It's all coming back. But we have reached this moment in the semester that we've probably been looking forward to for quite a while, which is that we have learned enough linear algebra now to go back to the differential equations. These last two chapters of the semester, I think I have what, about 6 lectures left or something? Not very many. These last lectures of the semester to go back to the differential equations again. However, I want somebody to start their stopwatch and see how long it takes before I'm already talking about linear algebra again. It's not going to take very long. Okay, he's going to actually do it. Okay, we'll get an answer in a second, but it's going to be a very quick thing, right? The idea here is we're going to try to use all of that material that we've learned to help us with our study of differential equations. Now, back in the beginning of the semester, we did study differential equations of order 1. That's where we had those Bernoulli equations and, the first order linear equations with integrating factors and all that stuff. So we did get our feet wet a little bit at the beginning of the semester with this. But now we're gonna go all the way up to an nth order linear differential equation. And if you harken back to before you even met me, I had you watch some videos at the start of the semester. Well, one of the things that you saw that very first week of the semester was what the form of a linear differential equation is. It basically looks like this, guys. You have the unknown function y along with some of its derivatives, and those different derivatives occur in different terms on the left side. Notice that we're not combining things. You don't see y being multiplied by y prime. That does not happen, right? You see y here, you see y prime here, you see y double prime here. They're all in different terms with coefficients in front of them that can be functions of x. Those functions of x could be anything, actually. So they don't have to be what you think of as traditionally linear functions. These coefficients could be trig functions. They could be exponential functions. They could be rational functions. There's lots of possibilities for the coefficients, but the way the different derivatives of y are laid out on the left side, that is non-negotiable of a linear differential equation. They must be laid out like I've expressed it here, right? Okay, and then on the right-hand side, you have some function f of x, which again, could be anything. It could be anything. Okay, so there's the equation that we're gonna be working with in chapter 8. Our goal is going to be to solve this differential equation. That's probably usually the goal when you're working on differential equations. To help us do that, I'm gonna try to rewrite this differential equation in a slightly different form. So I've got some notation here I just jotted down during the break. I'll be talking about an interval I, which is just some subset of the real number line. Not really a big deal. It's not going to be something we need to get too worried about, but this interval sometimes will be limited by the functions that you see. Maybe you can't divide by 0 or something. Okay, so then the domain shouldn't have 0 in it. Or square roots of negative numbers, things like that we have to kind of stay away from. So we're going to choose an interval such that everything makes sense in our equation. That's basically the idea. And here we're looking at the functions. This is C super K of I. These are the functions that are differentiable up to K times or more. So sometimes you can take a derivative of a function for a while, and then after that you can't take it anymore. So there might be a certain value of K that you're allowed to do. Again, this is not that big of a deal. I just am going to use this notation briefly in a few moments, but it's not really the main point. I will say that C super K of I, these K times differentiable functions, they form a vector space. Oh, what's my time?
2:49.
3 minutes and 49 seconds. I was talking slow. Yeah, that wasn't that long. Vector spaces are actually going to be a big part of what we're going to be talking about. Okay. So these things form vector spaces. Now, I am going to also try, as I said, to give us a little better notation for this. And to do that, I have a definition here. And I want to define this operator, guys. I'm going to define capital D. And this is going to be an operator that plugs in something from C1 of I and outputs something from C0 of I. So these are 1 times differentiable functions, and then just spitting out some function, right? Via D of F equals F prime. Right. And then, so in other words, it's really just a derivative operator. So D is equal to a derivative operator. That's the way I can think about that. It's a derivative operator, but moreover, or more generally, we can do D to the K of F. and we can spit out k derivatives of f. Sorry, not k derivative, the case derivative of f. So this is again, an operator that plugs in a function and spits out another function. So this looks like inputs and outputs. Have we seen that anywhere recently? What was it called? Linear transformations, right? Is this thing gonna respect addition and scalar multiplication? If I take derivative of f plus g, is it the same as the derivative of f plus the derivative of g? I sure think so, right? And if I have a scalar in front of this f, right, and I take the derivative of a constant times a function, can I pull the constant out? Does that work with derivatives? It absolutely does, guys. This d, I just want to note that this d, along with d squared and d cubed and any of these powers of d, these are all linear. So here we are talking about linear transformations already, right? That d is a linear transformation. Okay. Now, using that d notation, I can rewrite my original nth order form of my differential equation using the d notation. So I'd like to do that for you guys. The nth order linear differential equation in d notation. So I'm just going to call it d notation. You'll know what I mean. I'm going to write it out using the d notation. I'm also, as I'm doing this, I'm also going to suppress the x's. So I'm not going to keep writing the a naught of x and the a1 of x. I'm just going to write a naught, a1, a2. Okay, it's not a big deal. So on the left side, this is what I'm looking at, guys. Follow along with me here. I start off with a naught, and then I'm taking n derivatives of y. So that's going to be d to the n. Okay, and by the way, the of y, I'm just going to put that way over here. So a naught times d to the n of y. Remember, d to the n of y would just be y with n derivatives of it, which is what we see right here. Okay, the next term we're adding, we have a1 times n minus 1 derivatives of y. And we keep going like this, dot, 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 plus a sub n minus 1 times d. So this term here has just one derivative. And then finally, plus a sub n. And then all of that equal on the other side to f. There you go. That is your nth order linear differential equation rewritten using the d notation. The d notation just says, look, instead of actually writing a prime or a double prime or a triple prime, I'll just put a power of d that tells me how many derivatives I have to take. So if I give you a differential equation, right, as an example, if I gave you this differential equation, it's the same thing as d squared plus 1 of y equals 0. I can just translate from the prime notation to the d notation by turning derivatives into d's. See how that's working? I'm really sorry. I know we've just been doing all this linear algebra. Now suddenly I'm talking about something totally different. You with me? Go ahead.
What happened to the x's from our original form?
They are still there. So this a naught is just, I'm just suppressing the x to save space
Oh, I
to make
see.
it look pretty.
Right.
But it's really there. There's an a naught of x, there's an a1 of x, and so on.
Okay.
Yeah. Same thing on the right hand side. I just didn't write of x here, but it's really there.
Okay.
Yeah, it's really there. So far, so good. Now, I'm going to be even a little more lazy. I have all these sort of different powers of d, all of these different operators added together. I'm going to gather them all up into a single linear operator, which I'm going to replace with just L. So I'm going to call this whole left-hand side L. So we obtain, let's put this down here, L of Y equals F. Mathematicians have a way of using notation to take something messy and ugly and replacing it with something very compressed and simple. And the goal here, as you no doubt realize, is to solve this for y. Y is the unknown function that we're hoping to solve for. So capital F is given on the right-hand side. The L is the left-hand side of the differential equation, and y is just the unknown function that we are really going to be trying to solve for. Okay? Everybody so far so good? Let me just do a quick example. By the way, I will tell you, don't take this as a reason to slack off or anything, but I will tell you that most people find chapter 8 to be a little bit of a break. There's not gonna be a lot of vectors here. There's not a lot of matrices. It's gonna feel a little bit more like calculus again, even though I am, of course, interjecting my vector space concepts in here. It's actually, I think for a lot of students, they find this to be much more natural. You do have to take derivatives and do some things like that, but it's actually not so heavy on like the concept side. It's not nearly as heavy. So I hope that you'll enjoy that as a brief reprieve here in chapter 8 in that sense. Very different than what we've been doing in the last couple of chapters. Yeah. Just to give you an example, let me just make up an operator here. Let's let L equal x minus x squared times d squared plus the sine of x times d plus e to the x. This would be an example of an operator. And we can see here that this would be the A naught, and then this coefficient would be the A1, and this coefficient would be the A2. So you'd have just A naught, A1, and A2 in that setup. And I could ask you to compute L of, I can just make up something I want to do. Let's say I want to take L of x to the 10th. Okay, so this is just a basic example to kind of just show you what's going on with this thing. So if I ask you to plug in x to the 10th into this operator, what that really just means is you're going to plug this x to the 10th into this whole thing. So I have x minus x squared d squared plus sine of x d plus e to the x, right? So you could just put in what L is, right, or copy down what L was and then apply it to this. But all you're doing here, guys, you can literally just imagine distributing this. This is really my y value. I'm really just putting in, so this is y really, just playing the role of y there. I'm really just putting in this y value into each of these terms. So it's gonna be, x minus x squared times 2 derivatives of x to the 10th. And then plus sine of x times 1 derivative of x to the 10th. And then plus e to the x times x to the 10th. That's basically what it is. And I'm gonna do 2 derivatives of x to the 10th for you really quickly. It just turns into, I believe, 90 times x to the 8th. You take 2 derivatives of x to the 10th using the power rule. Excuse me, plus sine of x times 10x to the 9th. And then plus e to the x times x to the 10th. Okay. So that's just kind of how this L thing works. Just real briefly how that works. Okay. Now, it turns out that solving this equation here is a little bit harder than solving the same equation with a 0 on the right-hand side. Right? So just as a quick definition, the associated homogeneous is what the word is. The associated homogeneous nth order linear differential equation is L of y equals 0. In other words, if somebody asks us to solve this differential equation, we could instead sort of just forget about the f and put a 0 there instead, for the time being. Because this is easier to solve. Does anybody think they know why this might be easier to solve from a conceptual point of view, easier to solve than this one is? Well, I mentioned that the L is a linear transformation. Back in the 2 chapters ago, instead of an L, I would have called it a T. Right? And this Y is really my vector being plugged into the transformation. So this is going to be playing the role of V. If I wrote this equation down and I said, I'd like to solve this for V, what am I talking about here? No. Linear transformation. If I have T of V and I set it equal to 0, what am I solving for?
Closure by.
Say it again.
Okay.
The kernel of L. It is the kernel of L. That is exactly right, right? So the solutions to this, I love it. The solutions to this form the kernel of L, which I'm just going to tell you this. We don't have time to prove it, but I'm just going to tell you this. This kernel of L, it forms an n-dimensional vector space. The kernel of L forms a vector space. Just bear with me. I'm going to steal 2 minutes of your time because I'm so stoked about this. Okay? Extra, you don't even have to pay any extra tuition. Just going to go over this with you. This is super cool because I go back to my question. Why is this easier to solve than this one? It's because it's actually a vector space whose dimension we know, which means we know sort of how many solutions we need to come up with. Take a look at the example right here, guys. What's the n value for this equation?
2.
2, right? Does anybody think they can come up with 2 functions such that when you take 2 derivatives of it, and then you add it back to itself again, it becomes 0? Can anybody think back to your calculus days, guys? Is there any calculus function that you know that after you take 2 derivatives of it, you'll be up to the negative of what you started with?
Sine.
Sine and cosine. Yes. So this thing has 2 solutions. Write it down. Has solutions. Y1 of x, or call it cosine of x, and y2 of x, which is sine of x. Now, coming up with these 2 solutions is not the cool 250B part. You guys could have done this 1 second after you were in calculus, right? You didn't need any linear algebra for it. So what is the cool thing I'm saying right here? The cool thing I'm saying is that, well, if you didn't know this, that this was a two-dimensional vector space, you might wonder, oh, maybe there's more solutions. Maybe I should try, maybe something like this. Maybe if I miraculously took two derivatives of this, it would cancel itself back out and give me zero. I don't know, maybe. But wait a minute. What this is saying is that as soon as you have two basis solutions, did everybody notice that these are Li, by the way? They're not scalar multiples of each other. They are a basis. These are a basis for the kernel of L, which means that they span all of the solutions to the differential equation. Every solution, one last sentence and then we're done. I just have to get this in. Oh, I love this. Has the form some linear combination of that. Y of x equals C1 times the cosine of x plus C2 times the sine of x. You're building basically the span of the two solutions that you found. And there can be no others because this is only two-dimensional. It is only two-dimensional. You have two basis solutions here. So every solution is expressible as a linear combination of the basis. This is totally back to linear algebra again. But that's it. All right, I gotta stop. I'm so super stoked. I could go for another hour, but I got. Thanks, guys. Appreciate it. Thanks for being here today.
Every solution is expressed